This is the first of the grade 11 Cambridge Chemistry podcasts. There will be 16 of these podcasts, each taking care of one theme or one topic in the grade 11 curriculum. The first topic we will discuss is one that you're probably familiar with from your time in grade 7 and grade 8, and that is atoms and isotopes. The assessment criteria for this topic is as follows. You need to understand the evolution of 5 atomic models. You need to understand why isotopes are formed and their radioactive nature. You have to understand factors that influence the ionization energy, nuclear charge, and other atomic properties. You will also be able, by the end of this topic, to predict the influence of radioactive decay on the quantity of protons, neutrons, and electrons, and you will be able to interpret simple mass spectrum, learn how a mass spectrograph works, and find relative atomic and molecular mass of substances. There are 5 models that we will talk about in our study of atomic theory. They are the studies of Dalton, Thomas, Rutherford, Bohr, and the current model we rely on, the quantum mechanical model. The Dalton model said that elements consisted of very tiny things called atoms. It stated that an element is a kind of these particles. All the atoms that make up the element have the same mass, and all elements are different from each other because their mass is different. Thomson added onto this model. He came up with the plum pudding model. This is a Western reference consisting of a rather thick, milky substance. And in this thick, milky substance, or pudding, there are pieces of fruit, a plum, a cherry, other kinds of fruit. The electrons, as we know them today, were thought to be positioned throughout this atom, throughout this pudding. But there were many structures possible, so therefore there were many different kinds of atoms. Rutherford became a little bit more clear in his understanding of the difference between protons. It wasn't until about 1900 that the concept of electrons came about. So it's not surprising that after 1900, we would talk about electrons specifically and how they are related to the nucleus. Rutherford said that the atom was a tiny structure, it had a positively charged core, and negative charged electrons going somewhere around this positively charged core. Bohr's model in 1913, rather quickly after Rutherford, maintained that the electrons still went around these nucleuses, but they went in specific orbitals, specific levels, specific distances from the nucleus. The quantum model of the atom was designed and predicted in the late 20s, early 30s of the 1900s. And it said that these particle theories, all of the ones that came before them were particles, treating electrons, neutrons, and protons in little bits of substance that had mass. Well, the quantum theory stated that matter has also some wave properties. They also said rather than having different orbitals or different distances from the nucleus, they had places where electrons might be. They came up with the 4 quantum numbers, and those 4 quantum numbers are used currently to identify any electron going around any atom. The first is the principal quantum number, then the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. We'll talk more about these in class. Let us now turn our discussion to the topic of atoms and isotopes within the quantum model. Isotopes are atoms of the same element with different mass. They have these different masses based upon the number of neutrons. The atoms are based on the number of protons that we find in the nucleus. Now, different atoms have different isotopes. Some of these have stable nuclei. Some of them have unstable nuclei. The ones with unstable nuclei are called radioactive, and they tend to break down over time to more stable isotopes. So the original isotope, or the parent isotope, has some loss of particle or wave, and then we have a new isotope, or the daughter isotope. Let's look at a video that describes atoms and isotopes in much greater depth than I have just given to you.
The identity and chemical properties of any atom are determined by the numbers of protons in its nucleus. As atoms get bigger and heavier, the nuclei get bigger and heavier, and the protons need a sort of nuclear glue to help hold them together. Neutrons provide this glue and prevent the positive charges of protons from repelling each other, thanks to something called the strong nuclear force. Elements can exist with slightly different numbers of neutrons, and we call these isotopes of an element. It is particularly common for heavier elements where a lot of neutrons are required to hold the nucleus together, but smaller and lighter examples include the isotopes of hydrogen. Hydrogen-1, hydrogen-2, also called deuterium, and hydrogen-3, also known as tritium, are the 3 isotopes of hydrogen. They have 0, 1, and 2 neutrons respectively. Tritium is the heaviest isotope of hydrogen as it has a larger mass number. Note that in each of these isotopes there is a single proton. This means that the element is unchanged, and that's the important point. It is still hydrogen and will react chemically in exactly the same way. There is often more than one stable isotope of an element. In fact, much of the world around us is made up of stable isotopes. However, sometimes there aren't enough neutrons in a nucleus, or there may be too many for it to be stable. An analogy is a person carrying boxes. If you try to carry too many boxes, you'll end up dropping some. And if you continue, you'll keep dropping boxes until you reach a manageable amount. This is your stable state. And nuclei behave in a similar way, and they will try to stabilize themselves. If there are too many protons or too many neutrons, the nucleus can spontaneously rearrange itself and throw out particles in the process. This is essentially what happens in radioactive decay. Isotopes that have unstable nuclei like this are known as radioactive isotopes or radioisotopes. In our hydrogen examples, both deuterium and tritium are unstable and are hence radioisotopes of hydrogen. The more unstable a nucleus, the faster it will try to rearrange itself into a more stable state. And another name for this process is radioactive decay. Radioisotopes are often used in medicine to trace aspects of body chemistry or blood flow. For example, a small amount of the radioisotope technetium-99 may be injected into the bloodstream to show up on medical imaging and X-rays, and this is known as a medical tracer. Tracers can be used by chemists to understand how a reaction works. Atoms of radioisotopes can act as markers, allowing chemists to follow how a reaction sequence occurs. And of course, radioisotopes are also used in radiotherapy to kill malignant cancer cells.
Another of the assessment criteria is to be able to interpret simple mass spectrum. In order to do that, you must understand how a mass spectrometer works. If you look at the left side of this slide, you will see the 5 basic parts of an mass spectrograph. The first is the location where the thing to be tested is placed. In area 2, there is an electron gun. It heats up, it excites the atoms that have been placed in the machine, and it creates ions. In position 3, those ions are spread into, much like you would call a stream of ions, a very narrow stream. That narrow stream is then shot through an electromagnet. The magnetism of the electromagnet affects the charge on the ions. And the heavier the ions, the more it will bend in the electromagnet. In position 5, we see a location where we can measure or see a picture of the ions and how they have been spread by the electromagnet. When a mass spectrograph ionizes the substance that has been put in the machine, it ionizes everything it sees. And depending upon the length of the carbon compound, for example, that we look at, it will tend to break sigma bonds. On the right side of the slide, you see lots of different numbers, and those numbers correspond to what is called fragments that might come from the breaking of a carbon compound. If you look at 15, that is 1 carbon atom and 3 hydrogen atoms. That, if you had a longer carbon compound, maybe one of the fragments would be this. Maybe it would be 29, 2 carbon atoms and 5 hydrogen atoms. And you can see all these variations upwards into the 90s in terms of fragments, depending upon the length of the carbon compound that has been placed in the mass spectrograph. On the right here, you see a mass spectrum. Look at the line furthest to the right. If you notice, this is a mass spectrum of ethane. 2 carbon atoms and 6 hydrogen atoms. If you mass out ethane, it comes to 30. Notice the furthest line to the right. It is 30. That is the mass of ethane. All the other lines you see are fragments of that molecule that were ionized when the substance went through the ionization chamber. You see a 15 line, you see a 14 line, you might see a 28 line. Those are all fragments or pieces of that ethane molecule. As a part of this unit, we're going to look generally at some of the factors that influence a number of properties of different atoms on the periodic table. Later, we will talk about them based upon electron configuration, but we will need to first understand some of these factors. The first factor that needs to be understood is nuclear charge, and that is the charge in the nucleus. The larger the nuclear charge, for example, the greater the ionization energy. We also need to understand the radius of an atom. How does that change in groups or across the periodic table or in periods? Or as we go down the periodic table, what is the effect of the radius increasing or decreasing? We'll also talk about filling of the electron shells. That's what sublevel is. And shielding effect, we will talk about as atoms get as atoms get larger and larger, the ability of the innermost electrons to be invisible to the outermost electrons, and therefore the effects of the nucleus become less. That is called shielding effect. Now we can predict the influence or the trends in radioactive decay depending upon the number of protons, neutrons, and electrons that are in an atom. You'll see to the right a picture, and the red rose-colored band is called the band of stability. This is the area where we find isotopes to be generally non-radioactive. If you look at the first 20 elements, you can do that by looking along the x-axis, and you see the number of protons. You see that that follows a 1-to-1 proton to neutron ratio. But as the size of the atom increases, we see that this band of stability has a increasing ratio of neutrons to protons. We've got a couple questions here to start your thinking. Take a look at these questions and answer them if you need to redo a formative exercise.